With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello students, the question is, why is beta-D-glucopyranose the most abundant of naturally occurring aldohexoses? Okay, and your B part is, write the most stable chair conformer for alpha-D-fructopyranose. How does it differ from beta-anomer? Okay, so now let's see the answer. Let's see the first part, that is A. It says, why is beta-D-glucopyranose the most abundant of naturally occurring aldohexoses? So here, let's see the structure of beta-D-glucopyranose. The structure is, it's like this. Glucopyranose means, that means it is found from glucose molecule. Pyranose means it is a 6-membered ring. Okay, it is a 6-membered ring. Okay, so let's see. Beta-D-glucopyranose, the structure is something like this. Here. You will get oxygen here. Okay, this is your oxygen. Here. Okay, I have highlighted this because this is oxygen. This is not carbon, okay? You will get this. Alright, so here, because it says it is your beta-D, beta means the OH will be above the plane. So here your OH will come because this is your carbon number 1. You can say this is 2, this is 3, let's say 4, and this is 5. Okay, so, and one of the 6th one will come over here, CH2S. I'll just write it. Okay, OH, then another one will be here H. Now here, your OH and your H here, your OH, your H, alright, your OH and your H. Here, if you see, it is your hydrogen and here it is your CH2OH. So this is your 6th carbon, alright. So if you see this, if you see the structure like that, it is like this. Here your oxygen is there, which I have highlighted here. Okay, here it is like this. Okay, OH, H. Okay, here your OH is downwards. Here your OH is above. Here your OH is downwards. Here your CH2OH is there. CH2OH. Okay, this is the structure for your beta-D-glucopyranose. So now if you see here, why this is most abundant aldohexoses. Aldohexoses means any any kind of a sugar which has 6 carbons. Hex means 6 carbons with an aldo group. Aldo group, that means aldehyde. So any sugar containing 6 carbons and one of the carbons is an aldehyde group. So those sugars are known as aldohexoses. Okay, so here this is the structure for your beta-D-glucopyranose. And why it is stable? Because if you see all the OH and any bulky group, that is CH2OH, I mean, okay, they all are at equatorial positions. Okay, because all the rings substituent, any substitution that is there, OH, right, CH2OH, they all are at equatorial position. Equatorial means here this is at equatorial, this is also at equatorial, this is also at equatorial, and CH2OH is also at equatorial. Because all those conformers of all these conformers like this, wherever the most stable conformer is always the one where the substitution is present at equatorial position. If the substituents are always present at equatorial position, alright, so those conformers are always more stable. Alright, because here all the substituents are present at equatorial position, that's why this naturally occurring beta-D-glucopyranose is the most abundant. Why? Because it is more stable. Why it is more stable? Because all the substituents are present at the equatorial position, thus there is no steric hindrance. Alright, no steric hindrance is there. No 1,3 diaxial interaction is there. 1,3 diaxial means, let's say this is an axial group. Alright, so this is your 1, 2 and 3. So here your axial group will not be affecting it. Okay, let's say if I give you an example of this hydrogen. So 1, 2, 3. So this hydrogen will come downwards here, right? So it will not repel it because H and H are very small. They will not hinder each other. Similarly, 1, 2, 3. So this H and this H, because they are very small, they will not repel each other. They will not apply or put any steric hindrance. So that's why this compound will be stable, because there will be no 1,3 diaxial interaction, no steric hindrance, and of course substituents. And why no steric hindrance? Because there are substituents are present at equatorial position. Alright, so thus this is your most stable and most abundant conformer. Okay, this part is clear. Now let's go to the B part, that is write the most stable chair conformer for alpha D fructopyranose. Okay, we need to write the most stable chair conformer for alpha D fructopyranose. Okay, and how does it differ from beta anomer? So let's see. First of all, you should know what are anomers. Okay, so what are anomers? Anomers are nothing but they are type of, you can say they are type of the conformers only. It's a type of geometric variation found at only one atom of the carbohydrate molecule. Okay, so I'll explain it to you and I'll show you the structure. So let's see. We have to write the alpha D fructopyranose. Okay, so the structure of alpha D fructopyranose, if I show you, it is something like this. Chair conformer I'll show you. I'll show you the cyclic structure. Then I'll show you the chair conformer. Okay, so this is the cyclic structure. Oxygen is there, right? Here it is like this, alpha D. So that means your alpha means your OH will be below the plane. Below the plane, that means your OH is here. So this is your carbon number 1, 2, 3, 4 and 5. Okay, 6 is here, CH2H. So here if you see, this will go like this, OH. Here OH will be above the plane on second carbon, then on third carbon it will be downwards. On fourth carbon again it is downwards. And your fifth carbon will be CH2. So both the hydrogens are there. Okay, so I don't need to show that. Okay, it's well understood that hydrogens are there on this carbon. Okay, so this is the structure of alpha D fructopyranose. Now again, alpha means this OH is below the plane. Alright. D means that if you draw the single structure, D means if you draw the chain single structure, then your OH of the last second carbon, or you can say the last chiral center's OH will be on the right side. Okay, and fructopyranose means, fructo means there was a fructo, that means a keto group was there, like in the fructose. Okay, just like in the fructose. So it's fructopyranose. Basically, this is the cyclic structure of fructose only. Okay, and pyranose means a 6-membered ring. Okay, so now this is your fructopyranose. Okay, this is your alpha D fructopyranose. Now let's draw this, its cyclic conformer like this. So if you draw it like cyclic conformer, you will be drawing it like this. Chair conformer, I mean to say. Here it will go above here, and then here oxygen will come here, right? Here oxygen, then it will go downwards, and then it will go here. So this is your chair conformer, right? This is your chair conformer. So let's say this is your carbon number 1, this is 2, this is 3, this is 4 and this is 5. So your 5 was CH2. At carbon number 1 you have CH2OH above the plane. So it will go at equatorial position and your OH below. Similarly at second carbon you have it above. That means here on the axial one. Like this. Right? On third carbon it is below. So you will draw it below. Okay, it is understood that another one is hydrogen here. Okay. Another one is hydrogen here also. Now on carbon number 4, it is still below. So, I mean downwards, below the plane. So, why I am saying below the plane? Because this ring is in the plane. So, if this ring is in the plane, then this OH will be below the plane and this CH2OH will be above the plane. Okay. So, because it is below the plane, so I will put it as equatorial, then anaxial, then that means above the plane hydrogen will be there. Similarly here, at the fifth carbon, if you see, it is CH2. So both of them are nothing but hydrogen. Okay. So this is the structure of your alpha D fructopyranose. Okay. FP is nothing but fructopyranose. So alpha D fructopyranose. Now we need to tell that how does it differ from beta anomer. As I told you just now, that anomers are nothing but these are the structures which have a different configuration just at one carbon. Just at one carbon. So what will happen? What will be the difference in this structure and in your beta anomer of this fructopyranose, it will just be at one carbon, that is at this carbon. What will happen here? This OH will be above the plane. That's it. So if I write the cyclic structure first, so it will be like this I'm writing the cyclic structure of beta D-fructopyranose. Okay, that means the beta ionomer of alpha D-fructopyranose. So you will write it like this. Here OH, here CH2OH. This OH will remain above, and the rest, all the substitutions are same. This is your H, this is your OH, and this is your CH2. Okay, so let's draw the structure, the cyclic ionomer. How does it differ? That means at carbon number 1, if you see carbon number 1, the OH is above the plane in the beta ionomer, whereas in the alpha ionomer, of alpha D-fructopyranose, the OH is below the plane. In alpha, it is below the plane. In beta, it will be above the plane. So here OH will come. Here your CH2OH will come. Okay, that's it. The rest is completely same. Your OH here is at axial. Here also it is at axial. Here it is at equatorial. And this is your hydrogen. Okay, the rest is like, here it is hydrogen. Here it is hydrogen. Here it is hydrogen. And these also has hydrogen only. So this is the structure of your beta ionomer, and this is the structure of your alpha D-fructopyranose. Alright, so how do they differ? They differ only at carbon number 1. That means at this carbon number 1 here and here, in the alpha ionomer of fructopyranose, the OH is below the plane because it is alpha. Alpha means below the plane, right? And beta, in beta ionomer, this OH group at carbon number 1 is above the plane. Because beta means above the plane, right? So this is how your alpha and beta ionomers differs of fructopyranose. Okay, so I hope you understood. Thank you so much.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut App today.